There's a version of reality that physicists have known about for nearly 100 years, and almost nobody talks about it at dinner. Not because it's classified, not because it's too complicated for ordinary people, but because if you really sat with what it implies, you'd have to rethink something far more uncomfortable than science. You'd have to rethink yourself. Here's the thing about quantum mechanics that gets buried under equations and Nobel lectures. It doesn't just describe how particles behave. It describes the conditions under which anything can be said to exist at all. And every time physicists have pushed that question to its edge, every time they've asked, but what is the particle doing when we're not looking? Reality has given them an answer that should have made the whole conversation stop dead. It didn't. Science moved forward. Textbooks were written. Degrees were granted. And quietly, at the foundation of all of it, sat 8 paradoxes that nobody fully resolved. 8 places where the universe looked back at the people studying it and said, "You're asking the wrong question." That's what this is about. Not a lesson in physics, not a guided tour through equations you'll forget by tomorrow. This is something closer to an investigation, the kind that starts with a strange observation, follows it honestly, and ends somewhere you didn't expect to be when you pressed play. The strange observation is this: the deeper science looked into matter, the less solid matter became. And the less solid matter became, the more the act of looking seemed to be part of the problem, or part of the answer. That distinction, problem or answer, is the first thing we need to hold loosely, because quantum mechanics doesn't resolve it. It lives inside it. You'll encounter 8 paradoxes in this video. Each one is a real fracture in the classical picture of reality, the picture most of us were handed in school and never questioned, because it worked well enough for driving a car, signing a mortgage, and making sense of Monday morning. But well enough for Monday morning is not the same as true. And somewhere in the back of your mind, maybe not loudly, maybe just as a persistent low-frequency hum you've never quite named, you've suspected that the model you were given doesn't fully account for what you've experienced, that the certainty you were supposed to feel by now hasn't arrived, that the rules you were taught might not be the only rules. They aren't. These 8 paradoxes won't hand you a replacement model. What they'll do is something more useful. They'll show you exactly where the old one breaks, and in that breaking, if you stay with it, something opens. Not peace, not answers, clarity. There's a specific kind of person who finds their way to a video like this. Not someone chasing novelty, not someone looking for a shortcut to wisdom. Someone who has lived long enough to know that the official explanations, the ones handed down in classrooms and reinforced by decades of practical life, don't quite cover the full territory of being human. Someone for whom the word certain has become quietly a little suspicious. If that's you, you're in the right place. The loop we're opening right now, the rules you were never taught, won't close until the end. That's intentional, because the closure isn't a fact you'll receive. It's a recognition you'll arrive at, and recognitions, the real ones, take time to form. So let's begin with the most unsettling thing physics ever discovered. Not a particle, not a force, not a new dimension of space. An observation, just an observation. And what that observation refused to leave intact. Before the paradoxes, there's a problem. A single, strange, foundational problem that makes all 8 of them possible, and makes all 8 of them personal. It goes like this. In classical physics, the physics of Newton, of billiard balls and falling apples, of the universe as a vast clockwork ticking forward whether anyone is watching or not, the act of observation was irrelevant. You could, in theory, watch a system perfectly without disturbing it. The moon doesn't care if you're looking at it. A falling stone doesn't adjust its trajectory because someone happens to be watching from a window. Reality, in that model, proceeds independently of whoever is witnessing it. That assumption felt so obvious it was never really stated. And then quantum mechanics walked in and dismantled it completely. Here's what the experiment showed, and we'll get into specific paradoxes shortly, but stay here for a moment because this is the philosophical ground everything else stands on. When physicists began examining matter at the subatomic level, at the scale of electrons, photons, and the basic building blocks of everything you've ever touched, they found that these entities didn't behave like tiny billiard balls following predictable paths. They behaved like possibilities. More precisely, before measurement, a quantum particle doesn't have a definite position, a definite speed, or a definite state. It exists in what physicists call a superposition, which simply means a simultaneous layering of all its possible states at once, each weighted by a certain probability. It's not that we don't know which state the particle is in, it's that the particle, in any meaningful sense of the word, isn't in a single state yet. And then you measure it, and it is. This is not a limitation of our instruments. It's not a gap in our knowledge that a better microscope would fix. The mathematics of quantum mechanics, the most precisely tested theory in the history of science, accurate to 1 part in a trillion in some experiments, describes this not as an inconvenient measurement artifact, but as the actual structure of reality at that scale. The act of measurement doesn't reveal a pre-existing state, it participates in creating one. Read that again, slowly, because it doesn't get easier the second time. If that's true at the level of particles, and the evidence says it is overwhelmingly, repeatedly, across every laboratory that has ever tested it, then the clean separation between observer and observed, between the one who looks and the thing being looked at, is not a feature of reality. It's a story we tell, and this is where the philosophical problem stops being a laboratory curiosity and lands directly in your life. Because you have spent decades making decisions, forming beliefs, building a self-image, all on the assumption that you can observe your own life from a neutral position. That introspection is simply looking inward, the way you'd look at a clock on the wall, that the self you examine is already there, fixed and waiting, and your examination merely reports what it finds. But what if looking inward changes what's there? What if the self you examine is, in some non-trivial way, shaped by the act of examination itself? This isn't a metaphor borrowed loosely from physics to dress up a self-help point. The philosopher William James noticed something structurally identical to this in the 1890s, long before quantum mechanics existed, when he wrote about the stream of consciousness and observed that the moment you try to catch a thought in the act of thinking it, the thought changes. You don't observe the stream from a riverbank, you step into it, and the stepping is part of what the stream becomes. Not observation, participation. This distinction, not passive reception but active co-creation, is the philosophical hinge that makes all 8 paradoxes more than intellectual curiosities. It makes them mirrors, and mirrors are only useful if you're willing to look at what they actually show, rather than what you expected to see. Here's the second loop opening now, and it's worth naming clearly so you can track it. What does it mean to know anything if the act of knowing alters the known? This won't be answered in this block. It can't be. But hold it close, loosely, not gripped, because every paradox we walk through is, in some way, a different angle on this same question. The measurement problem, as physicists formally call it, is the technical name for this unresolved tension at the heart of quantum theory. After nearly a century of the most rigorous scientific work humanity has ever produced, there is still no consensus among physicists on what actually happens when a quantum system is measured. There are interpretations. There are competing schools of thought. There are brilliant people who dedicated entire careers to this question and died without agreement. That's not a failure of science. That's science being honest about where its tools reach their limit. And at that limit, something unusual happens. Physics starts to sound less like a manual and more like a koan, one of those short, paradoxical questions used in Zen practice, not to be solved, but to be sat with until something in the sitter shifts. What is the sound of one hand clapping? What is the position of a particle that has no position? Same structure, different century, same invitation. The invitation is not to abandon reason. It's to follow reason all the way to the edge of what reason can touch, and then notice what's still there past the edge waiting. 8 paradoxes are waiting. Each one is a door. Each one opens onto something slightly different, but they all share the same foundation. The universe at its most fundamental level does not behave the way you were told. And knowing that, really knowing it, not just filing it away as an interesting fact about physics, changes something about how you stand in your own life. This resolves any question about whether you need a physics background to be here. You don't. What you need is something rarer and more difficult, the willingness to be wrong about something you've held for a long time without knowing you were holding it. That's harder than any equation, but you've done harder things. Let's go through them. Not as a list. Lists flatten things that need to stay dimensional. as a sequence of breaks, each one deepening the crack that started with the one before it. Paradox 1. The double-slit experiment, where matter refused to be only matter. In the early 1800s, Thomas Young fired light through two narrow slits in a barrier and watched what appeared on a screen behind it. Instead of two bright lines, which is what you'd expect if light were made of discrete particles, the way tiny bullets would make two neat marks, he saw an interference pattern. Dozens of alternating bright and dark bands, the unmistakable signature of waves overlapping and cancelling each other. Light, it seemed, was a wave. Fine. Settled. Except a century later, physicists discovered that light also arrives as discrete packets of energy, particles called photons. So they ran the double-slit experiment again, this time firing photons one at a time, eliminating any possibility of waves interfering with each other. One photon, one moment, one journey. The interference pattern appeared anyway. A single particle, traveling alone, managed to interfere with itself, as if it had simultaneously passed through both slits, explored every possible path at once, and only when it struck the screen did it decide where to land. But then physicists added a detector at the slits, a device that would simply record which slit the photon passed through. The interference pattern vanished. The moment they looked, the photon behaved like a particle with a single definite path. The moment they stopped looking, it spread out like a wave across all possible paths. The act of observation, the simple presence of a measuring device, even one that never touched the photon directly, collapsed the range of possibilities into a single outcome. Reality changed because someone checked. This is not philosophy. This is a reproducible laboratory result, confirmed across more than a century of experimentation, in dozens of countries, with increasingly sophisticated instruments. It is among the most tested phenomena in all of science. And it has never been fully explained. Paradox 2. Schrödinger's cat, where the absurd became the formal. In 1935, Austrian physicist Erwin Schrödinger became frustrated with the implications of his own equations. To expose what he saw as an absurdity lurking inside quantum theory, he proposed a thought experiment, a hypothetical scenario designed not to be run, but to be reasoned through. Place a cat in a sealed box. Inside the box, connect a tiny amount of radioactive material to a poison release mechanism. If a single atom decays, a quantum event, fundamentally random, unmeasurable from outside, the poison is released and the cat dies. If the atom doesn't decay, the cat lives. Now close the box. According to quantum mechanics, the radioactive atom exists in superposition, simultaneously decayed and not decayed until it is observed. Which means, if you follow the logic honestly and without flinching, the cat is simultaneously alive and dead until you open the box. Not alive or dead in some unknown way that you simply haven't checked yet. Genuinely, formally both, held in a superposition of outcomes that the mathematics describes with complete precision. Schrödinger meant this as a reductio ad absurdum, a proof by absurdity, a way of saying, surely the theory must be wrong, because this conclusion is impossible. He expected physicists to fix the theory. They didn't. Instead, most interpretations of quantum mechanics accepted the conclusion and moved forward. The cat paradox didn't reveal a flaw in the equations. It revealed how far the strangeness extends, all the way from subatomic particles up to cats and by implication, up to everything. And it revealed something equally important: how deeply reluctant we are to follow our own logic when it leads somewhere that overturns our comfort. Schrödinger built a trap for quantum mechanics. Quantum mechanics walked through it without slowing down. Paradox 3. The EPR paradox and quantum entanglement, where distance stopped mattering. In the same year, Schrödinger published his cat, Albert Einstein, together with physicists Boris Podolsky and Nathan Rosen, published what became known as the EPR paper. Its goal was structurally identical to Schrödinger's, to demonstrate that quantum mechanics must be incomplete because its implications were, in Einstein's view, physically impossible. Here's the core of it. Quantum mechanics predicts that two particles can become entangled, linked in such a way that measuring one instantly determines the state of the other, regardless of the distance between them. Separate the particles by a meter, a kilometer, a galaxy, the correlation holds. Measure one particle and find it in a particular state, and its entangled partner, wherever it is in the universe, will be found in the corresponding opposite state, instantly, without any signal passing between them, without any time for information to travel. Einstein called this spukhafte Fernwirkung, spooky action at a distance. He was not using the word spooky casually, he meant it as a critique. For Einstein, nothing could travel faster than light. That was non-negotiable, the backbone of relativity. If measuring one particle instantly affected another across any distance, then either quantum mechanics was wrong, or the universe contained hidden variables. Hidden information that the theory wasn't capturing, predetermined answers that merely appeared random because we couldn't see deep enough. He was certain it was the latter. He was wrong. In 1964, Irish physicist John Bell devised a precise mathematical test, now called Bell's theorem, that could distinguish between a universe with hidden variables and a universe where entanglement was genuinely instantaneous and non-local. Non-local meaning not bound by the constraints of location, not requiring a signal to travel through space. The experiments ran. They ran again. They ran with increasing precision across the following decades, culminating in what physicists call loophole-free Bell tests in 2015. Experiments so carefully designed that virtually every possible alternative explanation was eliminated. The results were unambiguous. No hidden variables. Entanglement is real. Two particles, separated by any distance, share a connection that operates outside the architecture of space and time as we understand it. When you measure one, the other knows. Not through any signal, not through any mechanism physics can currently name, but immediately, as if the distance between them is at some level not real. Einstein's deepest intuition about the universe was wrong. The universe is stranger than he was willing to accept. Paradox 4. The uncertainty principle, where precision itself became the enemy. In 1927, German physicist Werner Heisenberg published a result that sounds on first hearing like a complaint about bad instruments. But it isn't. The Heisenberg uncertainty principle states that there is a fundamental limit to how precisely you can simultaneously know certain pairs of properties about a particle, most famously, its position and its momentum, which is its mass multiplied by its velocity. The more precisely you know where a particle is, the less precisely you can know how fast it's moving and in what direction. The more precisely you pin down its momentum, the more its position dissolves into uncertainty. And this is the part that matters. This is not an engineering problem. It's not that our instruments are too clumsy, too loud, too intrusive. It's not that a better measurement device would solve it. The uncertainty is written into the mathematics at the most fundamental level. It is a feature of reality, not a limitation of our tools. The particle doesn't have a precise position and a precise momentum simultaneously. Both simply do not exist at the same time. This fractures something most of us carry without knowing we carry it. The assumption that reality is at its base fully determined, that everything that exists has a precise state, and our ignorance is merely practical, a matter of not yet having looked closely enough. Heisenberg's principle says no. At the quantum level, there is an irreducible fuzziness baked into the fabric of existence itself, not a fog that lifts with better lighting. The fog is the terrain. Precision is not just difficult. In certain combinations, precision is impossible by law. Paradox 5. The quantum Zeno effect, where watching something prevented it from changing. This one is named after Zeno of Elea, a Greek philosopher from the 5th century BCE, who constructed paradoxes about motion to argue, seriously, rigorously, that movement is impossible. His most famous, an arrow in flight at any single instant, occupies a definite position and is therefore at rest. If it's at rest at every instant, when does it move? The paradox was dismissed for centuries as wordplay. Quantum mechanics rehabilitated it. The quantum Zeno effect, confirmed experimentally, first clearly demonstrated in the 1970s and 1980s, shows that a quantum system that is continuously observed will be prevented from evolving. An unstable particle that would normally decay within a predictable time frame can be kept from decaying simply by measuring it frequently enough. Watch it constantly, and it freezes. The act of repeated observation holds the system in its current state, interrupting the natural progression toward change. Not watching, watching. Watching stops things from becoming what they would otherwise become. If you've ever suspected that the relentless self-monitoring that modern life demands, the constant checking, the perpetual assessment, the never-ending measurement of where you are against where you should be, might somehow be part of what keeps you stuck, the quantum Zeno effect will not comfort you. It will, however, confirm something. There are things that can only change when you stop watching them so hard. This paradox resolves one question cleanly. Yes, observation arrests quantum evolution, but it immediately opens a larger one. If the observer has this much influence over what unfolds, then who or what is the observer? That question is coming. We're not there yet, but it's building. Let's slow down for a moment. Not because the science gets harder from here, it doesn't, not really, but because there's a tendency, when moving through material like this, to stay in the comfortable role of the person receiving information, to let the paradoxes remain safely abstract. Fascinating, yes. Relevant to particle accelerators and thought experiments, certainly, but held at arm's length from anything that actually touches the texture of your daily life. That arm's length is exactly what the next three paradoxes are going to close. Then paradox 6, the wave function collapse, where possibility became singular and something was lost. We've touched on this already, but it deserves its own space because its implications run deeper than the double-slit experiment suggests. In quantum mechanics, before measurement, a particle is described by what physicists call a wave function, a mathematical object that encodes not a single state, but the full distribution of all possible states, each with its associated probability. The wave function is not a map of ignorance. It is a map of genuine possibility. The particle is, in a meaningful sense, everywhere it could be, all at once, until measurement forces a choice, and then the wave function collapses. That's the technical term, shows collapse, and it carries more weight than physicists typically acknowledge in polite company, because what happens at the moment of measurement isn't just that we gain information. Something is lost. All the other possibilities, the entire landscape of what could have been, vanish, not gradually, not partially, instantly and completely the moment observation occurs. One outcome, the rest gone. Now hold that image loosely and bring it somewhere closer to home. Every significant decision you've ever made operated by the same structure, even if the mathematics was different. Before the decision, there was a superposition, not of quantum states, but of possible futures. Every path still open, every outcome still weighted by its probability, every version of your life still technically available. And then you chose, or circumstances chose for you, and the wave function of your life collapsed into a single trajectory. What you rarely stop to examine is what that collapse cost, not as a source of regret. That's not where this is going, but as a fact worth sitting with. Every time reality becomes definite, it does so at the expense of everything it could have been. Definiteness is not free. It always costs possibility. And a life spent only in definiteness, only in the confirmed, the measured, the already decided, is a life that has paid a price it never consciously agreed to. The wave function collapse asks a quiet but serious question. Are you collapsing possibilities prematurely? Are you measuring before you need to, forcing outcomes into definiteness before the fuller range of what could emerge has had time to show itself? Observation ends possibility. That's not always wisdom. Sometimes it's just impatience wearing the disguise of clarity. Paradox 7. Quantum tunneling, where barriers stopped being final. Classical physics is unambiguous on this point. If a particle doesn't have enough energy to cross a barrier, it doesn't cross the barrier. It stops. It turns back. The barrier is real, the energy is insufficient, and the outcome is determined. This is the physics of walls, of limits, of the word impossible used with confidence. Quantum mechanics disagrees. Quantum tunneling, which simply means the ability of a quantum particle to pass through a barrier it classically should not be able to cross, is not a theoretical curiosity. It is a real, measurable, constantly occurring phenomenon that underlies the functioning of the sun, the operation of your computer's transistors, the mechanism by which DNA mutates, and the technology inside the flash drive sitting on your desk. The particle doesn't go over the barrier. It doesn't find a gap in the barrier. It passes through the barrier, emerging on the other side without ever having had enough energy to be on top of it. The mathematics works. The experiments confirm it. The mechanism remains at a deep level, philosophically unresolved. We can calculate the probability of tunneling with extraordinary precision, but a fully satisfying account of how a particle accomplishes this feat does not exist. What exists instead is the result. Barriers that should be absolute are not. And this is where the paradox becomes something more than physics, because you have encountered barriers in your own life that felt final, not merely difficult, final, the kind that classical logic describes with perfect confidence. You don't have enough time, enough money, enough credibility, enough energy, enough of whatever the specific currency of that particular wall demanded. And classical logic said, stop here. But quantum tunneling suggests that the relationship between energy and barriers is not always what it appears to be at the classical scale. That impossible is a word that describes the view from one level of resolution. At a finer level, at the level where the actual mechanics of change operate, the picture is different. Not every wall is a wall. Some of them are probability gradients, thick in the middle but permeable at the edges, for the right kind of motion in the right kind of moment. What would you attempt if you weren't certain that insufficient energy meant an absolute stop? Paradox. 8. The anthropic principle and the fine-tuned universe. Where the universe appeared to know someone was coming. This final paradox sits at the boundary between physics and philosophy, which is precisely why it belongs here, at the point where the other 7 have done their work of loosening the ground, and something larger can be asked. The observable universe operates according to a set of physical constants, numbers that determine how strong gravity is, how fast light travels, how electrons interact with atomic nuclei, how matter and antimatter were distributed at the beginning of everything. These constants are not derived from deeper equations. They are simply what they are, measured and recorded. Foundational in the way that the ground is foundational. You build on it without asking why it's there. Here is what physicists discovered when they began asking what would happen if those constants were slightly different. Not dramatically different, slightly. If the gravitational constant were a fraction stronger, the universe would have collapsed back in on itself within seconds of the Big Bang, before stars could form. A fraction weaker, and matter would have dispersed too rapidly to coalesce into anything. No galaxies, no solar systems, no planets, no conditions under which chemistry becomes biology. If the ratio of electromagnetic force to gravitational force differed by 1 part in 10 to the 40th power, a number so precise it strains the imagination, stars could not exist in the form required to produce the heavier elements that make up your body. The numbers that govern reality are set, across dozens of independent parameters, to values that permit the existence of complexity, chemistry, life, and observers. The probability of this occurring by chance, if chance even applies to the selection of physical constants, is, depending on how you calculate it, somewhere between vanishingly small and mathematically incomprehensible. Physicists call this the fine-tuning problem. The anthropic principle, which simply states that the universe we observe must be compatible with the existence of observers capable of observing it, is one response to this problem, though it raises as many questions as it answers. The multiverse hypothesis, the idea that our universe is one of an effectively infinite number of universes, each with different constants, and we simply find ourselves in one that permits our existence, is another response. Neither is fully satisfying. Neither is experimentally testable in any straightforward sense. What the fine-tuning problem leaves you with, if you engage it honestly rather than dismissing it as mere coincidence or retreating into dogma, is a question that has no clean resolution. Why does the universe appear configured for witness, not for comfort, not for fairness, not for happiness in any recognizable sense, for witness, for the existence of something that can look back at the universe and recognize it? This is the 8th fracture, and it is the deepest one. Not because it proves anything, it doesn't, but because it points in a direction that the other 7 have been quietly pointing all along. Every paradox we've examined has circled, from a different angle, the relationship between the universe and the observer. The double-slit experiment, observation changes outcomes. Entanglement, separation may be less real than it appears. The Zeno effect, watching arrests change. The wave function collapse, observation ends possibility and creates definiteness. Quantum tunneling, barriers are probabilistic, not absolute. The fine-tuned universe, the entire system appears oriented toward being observed. At some point, the accumulation stops being a collection of curiosities. At some point, the pattern becomes the point. Here's where we have to stop pretending the question is about physics. It never was entirely. Physics was the vehicle, the most rigorous, the most tested, the most empirically honest vehicle available for approaching a question that is ultimately about something closer and stranger than any particle. The nature of the entity doing the observing. Because every paradox we've examined rests on a word that has been left carefully undefined. Observer. In the double-slit experiment, the observer is a measuring device, a detector placed at the slits. It has no consciousness. It doesn't think. It doesn't choose. It simply interacts with the particle in a way that registers information, and that registration is sufficient to collapse the wave function, to end the superposition, to make reality choose. You don't need a human eye. You need an interaction that records. So the question becomes, what exactly constitutes an observation? And this is where physicists have been genuinely, seriously, unresolvedly divided for 100 years. One camp, associated with the Copenhagen interpretation, the framework developed primarily by Niels Bohr and Werner Heisenberg in the late 1920s, essentially says, don't ask. The wave function collapses when a measurement is made. Measurement is defined by its practical outcome, and asking what really happens beneath that is a question science cannot and should not try to answer. Shut up and calculate, as the informal motto goes. The formalism works. Use it. Another camp, associated with the many worlds interpretation proposed by Hugh Everett in 1957, says the wave function never collapses at all. Every possible outcome occurs, but in branching versions of reality that never interact with each other after the branch point. When you measure a particle and find it in a particular state, you haven't collapsed anything. You've simply become entangled with one branch of an ever-expanding tree of parallel realities, each one as real as this one, each one containing a version of you who found a different result. No collapse, no loss of possibility, infinite proliferation instead. A third camp, smaller, stranger, and in some ways more philosophically honest, takes seriously the possibility that consciousness itself plays a role in wave function collapse. This view, associated with physicists like John von Neumann and Eugene Wigner, and later with more speculative thinkers, suggests that the chain of physical interactions involved in measurement only terminates, only produces a definite outcome when it reaches a conscious observer, not a detector, not a recording device, a mind. This interpretation has fallen out of fashion in mainstream physics, partly because consciousness is itself so poorly understood that invoking it explains nothing formally. You replace one mystery with a deeper one, but it has never been definitively ruled out. And it has never stopped being philosophically provocative, because if it contains even a grain of truth, it means that consciousness is not a late arrival in the universe, a biological accident that appeared after 13 billion years of purely physical processes, but something woven into the structure of how reality becomes definite, not a product of the universe, a participant in it. What's at stake is the answer to a question you've been carrying your whole life without necessarily having the language for it. Am I in this, or am I of it? Are you a witness to a reality that would unfold identically without you, a spectator in a theater whose performance is indifferent to the audience? Or are you something the performance requires? Something without which certain things would remain, in a technically precise sense, undecided? The honest answer is, we don't know. But the shape of the evidence, the consistent, reproducible, mathematically rigorous evidence accumulated across a century of quantum experiments, keeps pointing in the same direction. The observer is not separable from the observed. The boundary between them is not where common sense places it, and the implications of that boundary being in the wrong place extend far beyond physics. They extend into how you understand memory. Because if observation participates in creating the present, what does it do to the past? Here's something that will land strangely at first. Quantum mechanics suggests, through a phenomenon called delayed choice, first proposed by physicist John Wheeler in the 1970s and later confirmed experimentally, that an observation made now can appear to determine what a particle did in the past, not predict, not correlate with, retroactively determine. In Wheeler's delayed choice experiment, the decision about whether to measure which path a photon took is made after. The photon has already passed through the apparatus, and yet the photon's behavior, wave-like or particle-like, matches whatever the later measurement would have required, as if the future observation reached back and shaped the past event. The past, at the quantum level, is not fully fixed until it is observed. This is not time travel. It doesn't allow you to change history in any practical sense, but it dissolves something most of us take as absolute, the idea that the past is sealed, finished, beyond the reach of anything happening now. At the quantum level, that sealing is conditional. It depends on observation, it depends on the observer. And here, the fourth loop, what is the observer really, reaches its partial resolution because the honest answer turns out not to be a definition, but an expansion. The observer is not a passive receiver, not a neutral recorder, not a ghost watching from behind glass. The observer is a participant in the ongoing process by which possibility becomes actuality, by which the smeared, probabilistic, superposed quantum world resolves into the specific, tangible, experienceable reality you wake up inside every morning. You're not watching the universe happen. You are part of how it happens. That's not a motivational statement. It's not an invitation to magical thinking or a license to believe that wishing makes things so. It is, as precisely as the current state of physics can say it, a description of the structural relationship between consciousness, or at minimum, between information registering processes, and the fabric of physical reality. And it changes something about how you might hold your own presence in the world, not your actions, not your achievements, your presence. The simple fact of your being here, attending, registering, participating in the act of observation, that the universe, according to the best science we have, appears to require in order to become fully real. There's a concept in Eastern philosophy, particularly in certain strands of Vedantic thought, that has been circling this same territory from a completely different direction for thousands of years. The Sanskrit word sakshi, which translates roughly as the witness, refers not to a passive observer standing apart from experience, but to the pure awareness within which experience arises, not a self that watches, awareness itself prior to the construction of a self. Physicists arrived at something structurally similar from the opposite direction, not through meditation, but through mathematics, not through stillness, but through increasingly precise experiments that kept returning the same uncomfortable result. The observer cannot be removed from the equation. In both cases, the ancient contemplative and the modern physicist, the conclusion is the same. There is no view from nowhere. Every observation is made from somewhere. Every measurement is performed by something. Every collapse of possibility into actuality involves an interaction, a contact, a meeting between the world and whatever is attending to it. And that attending, whatever its ultimate nature, is not incidental to what unfolds. It is constitutive of it. The universe needs a witness. You are that witness. This resolves the observer question at the level of function. What remains, and what the final blocks will carry, is the question of what that means for the specific person watching this right now, in whatever room they're sitting in, whatever they're carrying, whatever version of certainty or uncertainty they walked in with. That person deserves to be named directly. Let's step out of the framework for a moment. No more paradoxes, no more physicists, no more centuries and experiments and interpretations. Just this. You are somewhere between 45 and 70-something years old, roughly speaking, which means you have lived long enough to have experienced something that younger people mostly haven't yet. The moment when the model breaks. Not cracks, breaks. The moment when the way you understood yourself, your relationships, your sense of what was real and solid and dependable turned out to be less permanent than you'd built your life on the assumption of it being. Maybe it was a loss. Maybe it was a transition, a career, a marriage, a belief system, a version of yourself you'd identified with so completely that losing it felt like losing the ground beneath your feet rather than something standing on the ground. Maybe it was subtler than that. Maybe it was just the slow accumulation of evidence that certainty, the kind you were promised, would arrive by a certain age, the kind that was supposed to feel like finally having your footing, never quite came. That the longer you lived, the more the edges of things blurred rather than sharpened. If any of that is familiar, and I suspect it is, for the person who found their way to a video about quantum paradoxes on a Tuesday afternoon or a Sunday evening, or whatever quiet moment carved itself out of an otherwise scheduled life, then here is what I want to say directly to you. You weren't failing to understand reality. You were understanding it more accurately than the model you'd been given could accommodate. The blurring at the edges isn't a symptom of confusion. It's what reality actually looks like when you're paying close enough attention. The uncertainty that never resolved into the promised certainty isn't a personal failing. It's the texture of existence at the level where things are actually happening, as opposed to the smoothed-over, simplified version we hand people when they're young enough to still need the simplification. The quantum Zeno effect, watching something too closely prevents it from becoming what it needs to become, is not only a laboratory result, you've lived it. You've watched yourself so carefully, monitored your own progress so relentlessly, measured yourself against where you thought you should be with such persistent intensity, that the very watching became part of what held the thing in place. The wave function collapse, observation ends possibility, is not only a feature of subatomic particles. Every time you needed a situation to be definite before it was ready to be definite, before the fuller range of what could emerge had time to show itself, you collapsed something. Sometimes that was necessary. Sometimes it was just the discomfort of superposition, of not yet knowing, wearing you down until you forced an outcome simply to end the uncertainty. Quantum tunneling, barriers that should be final sometimes aren't, is not only a principle that explains your computer's transistors. You've tunneled. There were moments in your life when, by any reasonable classical calculation, the energy wasn't there, the credentials weren't there, the timing wasn't right, the circumstances didn't support the outcome, and it happened anyway. Not because you were lucky, because barriers at the level where actual change occurs are probabilistic. They have edges, and something in you, in the right moment, found one. You've been living inside these paradoxes the entire time, not as intellectual concepts, as the actual structure of your experience. The fifth loop, and you've been living inside these paradoxes, closes here. But it closes not as a resolution of something abstract, but as a recognition of something already true. You already knew at some level that reality was stranger than the official account. You already knew that observation changed things. You already knew that some barriers weren't final. You already knew that certainty was less solid than advertised. What you may not have had is the language for it, or the permission to trust what you knew. Consider this the permission, not to abandon reason. Reason is what got us here. But to extend reason past the point where it starts to feel uncomfortable, past the edge where it begins to sound like something other than reason, into the territory where the most rigorous science and the deepest human experience have been saying the same thing from opposite directions for a very long time. You are not a passive witness to a reality that would be identical without you. You are the kind of thing the universe appears to need in order to become what it is. That's not poetry. That's the best physics we have. Here's what the 8 paradoxes taken together are actually saying. Not separately. Separately, they're fascinating. Together, they're something else. Together, they constitute not 8 different problems, but one problem approached from 8 different directions, each time returning the same answer in a different form. The problem: what is the relationship between the observer and the observed? The answer in every case is the same. The boundary you assumed was there, fixed, clear, separating the witness from the witnessed, is not where you placed it, is possibly not a boundary at all in the way you understood the word. The observer and the observed are entangled, in the precise technical sense of that word, linked in ways that don't require proximity, that don't diminish with distance, that operate at a level beneath the architecture of space and time that classical physics describes so convincingly, that we mistook the description for the thing itself. Let's close the loops one by one, because open loops are a kind of debt, and this is where the debt gets paid. The loop anchor, the rules you were never taught, closes here. The rules you were never taught are not secret. They were never hidden behind a paywall or locked inside a graduate degree. They were hiding in plain sight, inside the most tested and confirmed scientific theory in human history, waiting for someone to follow them, past the comfortable stopping point, past the point where the equations become useful, and before the point where their implications become too strange to sit with. You've now sat with them. The second loop, what does it mean to know anything if the act of knowing alters the known, closes here too, but not with an answer. It closes with a reframe. Knowing is not a passive reception of pre-existing facts. It is a participation. It is a co-creation, however slight, however partial, between the structure of what is and the structure of whatever is attending to it. This doesn't make knowledge arbitrary. It makes knowledge relational. And relational knowledge, knowledge that includes the knower as part of what is being known, is not weaker than the classical kind. It's more accurate. The third loop, what would change if certainty was the illusion, closes in the most personal register. What would change is not your circumstances. What would change is your relationship to the discomfort of not yet knowing. Because if certainty was never the destination, if the universe itself operates on probability and superposition all the way down, if even the most fundamental particles exist as distributions of possibility rather than fixed points of fact, then the discomfort you've been trying to resolve by forcing outcomes into definiteness was never a problem to be solved. It was reality asking you to stay a little longer in the open. Not forever. Decisions must be made. Wave functions, metaphorical and literal, do collapse, but there is a difference between collapsing a possibility because it's time, because the fuller range has shown itself, because what's needed has emerged, and collapsing it because the superposition became unbearable and you needed it to stop. That difference is not small. It's the difference between a life that feels chosen and a life that feels like a series of forced conclusions. The fourth loop, what is the observer really? Doesn't close with a definition, it closes with an expansion. The observer is not a thing that stands apart from reality and watches. The observer is the process by which the smeared and probabilistic becomes specific and real. You are not separate from the world you're perceiving. You are, in some structural and non-trivial sense, part of how it is perceiving itself. The fifth loop, you've been living inside these paradoxes, closed in block 6. But its echo belongs here. Your life has not been a failed attempt to achieve clarity in a world that should have been clearer. It has been an honest encounter with the actual texture of existence. The confusion was not yours. The uncertainty was not a deficit. The edges that wouldn't sharpen were accurate. Now, the synthesis. All 8 paradoxes, the double-slit, Schrödinger's cat, entanglement, the uncertainty principle, the quantum Zeno effect, wave function collapse, quantum tunneling, the fine-tuned universe, are one paradox. The same one. Stated simply, in the 15 words this moment deserves, reality becomes definite through encounter, and you are always the encounter. That's not mysticism. That's not a motivational poster. That's the logical conclusion of a century of experimental physics, stated as plainly as the material allows. Reality, at its most fundamental level, does not resolve into definiteness without interaction. And you, the attending, the witnessing, the registering, the participating consciousness that woke up this morning and pressed play on a video about quantum paradoxes, are the form that interaction takes at the scale of a human life. The universe needed something capable of witness. It produced you, not you specifically in the sense of your name and your history and your particular set of accumulated certainties and doubts, but the capacity you carry, the capacity to attend, to observe, to be present to what is happening, is not incidental to the universe's project. It may be central to it, and that changes something, not loudly, not immediately, but in the way that real clarity always changes things, quietly at the foundation, in a place you'll notice later when you look back and realize the ground has shifted slightly beneath a life that looks, from the outside, exactly the same as before. If something in this landed, not as information but as recognition, The best thing you can do with it is not to share it, not to argue about it, not to build a new certainty out of it. Sit with it. Let it remain slightly open, the way quantum mechanics remains slightly open, the way every honest investigation of reality eventually must. The closure you're looking for isn't at the end of another video. It's in the quality of attention you bring to what's already in front of you. If you want to go deeper, into the philosophy of observation, into what the major interpretations of quantum mechanics actually say about consciousness and reality, into how thinkers from Bohr to Wittgenstein to the Vedantic philosophers have circled this same territory, that's what the next video is for. Leave a thought in the comments, not what you think, what shifted. There's a difference. And if you know someone who has been carrying the low-frequency hum of a reality that doesn't quite fit the model they were given, send this to them, not as an answer, as company. Reality becomes definite through encounter. You are always the encounter.